Hello everyone. Sorry for the hiatus. I was on vacation and then I got sick after my vacation. So then my throat was dead. But we're gonna pick up from, I guess, this will be X-ray diffraction. So then this would be a continuation of the second week. I didn't have enough time to go through, or I don't think we're gonna have enough time, so I'm just making this video. And then yeah, and hopefully you reviewed the Crystal Plains video linked that I linked in. The reason why I put that in is just so that you're familiar with the nomenclature. You're not like completely shocked when you see like say 111 or 001. They just refer to the different planes that you might see. Nothing too crazy. We're not going to delve into those that much. Yeah, so it's just so you're familiar with that notation. So let's just continue on. So X-ray diffraction. So before we go on to talk about the specifics of X-ray diffraction, let's just go over some basic wave physics. So waves and physics, because we all love physics, right? Anyways, so first we should talk about the basic anatomy of a wave. So if I were to draw one cycle of a wave, this would be the crest, which is essentially the highest peak. This would be the trough, which is the lowest part. And this distance would be the wavelength. The wavelength is essentially one complete cycle. One complete cycle of a certain wave. So for example, in a sinusoidal wave, um, so derived from y is equal to sine theta, this would be one cycle. If you have something like y equals cosine theta, it will look something like this. But in most cases, you're going to be working with sine waves. Sinusoidal waves are the most common ones. So don't worry too much about the cosine waves. Sorry about the echo. And yeah, so then this would be one wavelength. And essentially what a wave is in physics, or for our specific purposes, is that a wave is traveling energy in space. All right. So then that's some of the basics of waves. So just the basic anatomy of a singular wave. And so sometimes you might see some kind of device and it's propagating waves like this. However, what happens when we have multiple waves? What happens when waves begin to intersect and interact with each other? Well, we can see this perfectly with something called the double slit experiment. So the double slit experiment will basically tell us what happens um, when we have different waves intersect or intersecting each other. So the way that the double slit experiment is set up is that we have a light source and it's going to emit waves of light. And then you have a screen and you have these edges, these openings, these two openings that the waves can then pass through. And then a special property of waves is that they're able to diffract, which essentially means that once you hit those tiny waves or these tiny openings over here, let me do that in blue so you know that those are the openings. What happens is that you have two new wavelets that form. So the waves will start coming out of those holes. And then we essentially get two different waves of light. And then because as you see over here, inside the middle over here, we have some intersection going on. And then for the final part of the double slit experiment, we have a screen that will basically detect when light is hitting the screen. So what happens is that if lights say, let's just do this in green. Let's just say I have this slit over here. If light hits it over here, then it will record it as a mark and we'll be able to see different marks of light. So then when it comes to this double slit experiment, what essentially happens is that once we have these two waves intersecting each other, what actually happens is that we have alternating marks of light and darkness. So just pretend that this is the light. So bright stripes, and these are the dark stripes, the white space. So then that's essentially what happens when two waves intersect with each other. Now you might be wondering, well, why does that happen? Well, the reason why that happens is because if we go back to the anatomy of a wave, we just draw that over here, we see that waves have amplitudes to them. So then say that this is the midline, so y equals 0. This a over here is the amplitude. And the amplitude is what really determines the brightness. So for example, if I have a wave like this and a wave like this, they have roughly the same wavelength. However, this will be a lot brighter. This would be a lot brighter. Yeah. So then this would be a lot brighter and this will be darker. So essentially what happens here is that notice how these parts are intersecting each other. Well, if you know, or if you remember some math, I think you guys, or the majority of you guys will cover this in algebra. But if you're taking pre-calc right now, or yeah, if you're taking pre-calc right now or beyond, you guys would have already know this. But what happens is that at this yellow region over there, let me just draw that. At that yellow region, what actually happens is that we have two waves intersecting each other, interacting. So I have one wave over here, and let's just say if we want a bright light, what actually happens is that we have two waves that are in phase with each other. What I mean by in phase is that they're kind of aligned like that. So what actually happens is that the amplitude of this wave and the amplitude of this wave gets combined to get an even larger amplitude, thus resulting in a very bright stripe, which is detected with these dark strips that over here that are used to represent the light stripes. So some parts of waves, the lights or the waves are in phase, which means they become even brighter because the amplitudes are combined together. However, some other parts, and this will explain the dark stripes that we see, is that what happens, let me do this in blue or black. What actually happens is that these waves are not in phase. When I say not in phase, that essentially means that they're not really aligned with each other at all. So they're kind of like that. And say that this is y equals 0, y equals 0. So what happens over here is that say we have this part, which is a positive value. It doesn't matter. Let's just say positive x. And let's just say this part is negative x. They're going to be the same value. So then positive and negative x, well, if we take the logic that we had for the very first part, when it comes to determining the light stripes, we're basically adding the amplitudes together. So in this case, we had positive y. I'm calling it y as a reference, and positive y over here. Well, positive y plus positive y equals positive 2y. So it's an extra large amplitude. In this case over here, if we have positive x plus negative x, we get 0. So essentially what happens out over here is that these waves will cancel out each other. And once we have waves that actually cancel out each other, there is no amplitude, which means there is no brightness. So then that explains the darkness that we see over here with that white space. Now, okay, great. Why is this important? The reason why it's important is because if we go to X-ray diffraction, well, X-rays are on the electromagnetic spectrum and they are on the nanometer scale. On the electromagnetic spectrum, EMS, they are on the nanometer scale. And the reason why this is important is because this is the same scale as atomic separation. So it's on the same scale as atomic separation. Now, okay. So yeah, so let's just show an example of, I guess, what really happens inside X-ray diffraction. And I guess before we go on, I should probably introduce the fact that X-ray diffraction is used to determine the atomic spacing between atoms within crystal structures, which can then be used to determine the type of crystal structure that we have. Um, so for example, if you know the atomic separation, you can then use a certain formula and then do a whole bunch of math to figure out, okay, well, we have this crystal structure, and vice versa. You can figure out what kind of crystal structure you have and then figure out the atomic separation from there. So let's go look into the deeper parts of X-ray diffraction and what that looks like. So when it comes to X-ray diffraction, the way it works, let me draw this. Um, this will take a while to draw. And the points I'm drawing are the actual atoms within a crystal plane. You'll have to do. So these are the atoms within the crystal plane. And what happens is that once we shoot X-ray onto was it a crystal plane, what happens is that we get specular reflection. So specular reflection looks a little something like this. So we have the X-ray coming over there, X-ray, and it will reflect off this way. So it'll come at a certain angle, theta, and it'll reflect at the exact same angle, theta. And then we have another wave coming in this way. And again, specular reflection will then kick back, or kick in, I should say, and it'll come out this way. And then we have another one over here. Specular, no, that's not right. I could do that a lot better. This part's going to take a while because I always struggle with the third layer. There it is. That's a little better. So then we have the waves coming in this way. This will also come at theta, reflect at theta. It's a law within physics, within optics, is that if we have specular reflection, the angle of incidence will be the exact same as the angle of reflection. And again, over here, exact same angle going in, exact same angle going out. All right, so then once we shoot an X-ray onto a crystal structure within the planes, we're going to have specular reflections across the different planes. And I guess I should also specify in yellow that this refers to atomic distance or atomic separation. So DHKL. HKL refers to the plane. And this is the part where diffraction actually starts to come in, or I guess wave interaction. Because what happens here is that the machine or sensor then detects these waves going into it, and they were able to get results from there. However, the only way we can get results, or the only way that the sensor can actually detect the light, is if all of the light are in phase with each other. So reflected light must be in phase with each other. Because if they're not in phase with each other, then that means, say, for example, this wavelength might start canceling out with this wavelength, and then in the end, we're not going to have anything to detect for this, or the sensor is not going to have anything to detect. So that means the only way we can have some kind of detection is if all of these waves are in phase with each other. However, if we look at this atomic separation over here, we see that the atomic separation is important in determining whether the waves are in phase with each other or not, which means we can then say, yeah. So then what we can then determine from there, so I'm just reviewing my lecturing notes as I go along to make sure I'm not forgetting anything. The observed diffraction of atoms is a function of atomic separation. So knowing that this reflected light must be in phase, and we see that it is heavily determined by the atomic separation, we can then relate the two by a certain wavelength. So that we can then, say that the observed diffraction or the observed reflected wavelength is a function of the atomic separation. Atomic separation is very important in this case, and this is something called Bragg's law. And Bragg's law, if we're to essentially put it down as a formula, is that n, which is basically the order of a wave, which will be given to you, so don't worry about what that n is. So n could be 1, n it could be 2, n could be anything, whatever. N times the wavelength in nanometers is equivalent to 2 times the atomic separation, DHKL, times sine theta. Sine theta basically refers to both the angle of incidence and the angle of reflection. Remember, going back to physics, the angle of incidence must be the same as the angle of reflection. So this is Bragg's law and will be super important in determining the atomic separation and determining a whole bunch of necessary information we need in order to figure out crystal structure. All right, what's next? All right, so then this essentially describes what happens during X-ray diffraction. Let's look at what results from X-ray diffraction may look like. So let's do this in green because I feel like it. So the results from X-ray diffraction may look like this. So then you're going to have a graph that says intensity over here and 2 theta. The reason why it's 2 theta is because over here, when it comes to specular reflection, we have theta, angle theta, angle theta. So then combine the two is 2 theta. That's just the convention. What actually happens is that we will have different peaks that go across of we have different peaks that as theta increases, or 2 theta, I should say, intensity decreases. And then these peaks, each peak correlates to a different crystal plane. HKL value. Yeah. So then each of those intensities, each of those peaks will refer to a specific plane. And if you know what those planes are, you can then determine the crystal structure, which I will go over. But actually, yeah, let's just go over that right now. So determining, or was it depending on the types of peaks we get, we can then determine the type of crystal structure that we have. And the reason why we can do this is because of something called reflection rules. So reflection rules, was it states that some sets of crystallographic planes do not allow for diffraction to occur because we have out of phase scattering. Since waves will be out of phase. Yeah. So then the reflection rules given, if I were to draw a little bit of a graph, rules is that we have the crystal structure, reflection present, and the peaks or the planes. So then if we have a BCC structure, was it the H or the sum of the H plus K plus L must be even So then that means the indices of the first 6 planes, I should probably specify that. First 6 plane will then be 1, 1, 0. And we see that 1 plus 1 plus 0 is 2, which is even. 1, 1, 0, 2, 0, 0, 2, 1, 1, 2, 2, 0, 3, 1, 0, and 2, 2, 2. For FCC, was it? Ooh, you know what? It's fine. H, K, and L either all odd or all even. So then that means the first 6 planes will either be or will be 1, 1, 1, 2, 0, 0, and note that 0. Put that note somewhere. Note 0 is even. 2, 0, 0, 2, 2, 2, or 2, 2, 0, sorry. 3, 1, 1, 2, 2, 2, and 4, 0, 0. And then for simple cubic, well, all reflections are present. Oh, well, what's going on there? All reflections are present. There will not be any out of phase scattering. So then that means the first 6 planes reflected will be 1, 0, 0, 1, 1, 0, 1, 1, 1, 2, 0, 0, 2, 1, 0. Oh, did I reprint? Wait. Oh, sorry. 2, 1, 1. Sorry. I had a bit of a brain fart. Anyway, so then these are the reflection rules that will be super important in determining the crystal structure. And then you can then use that information to figure out other information. And I'll show you that very quickly. First, I'll just put that on the screen so that you can just quickly copy that down. Okay, I think that's enough time. I just realized you can pause videos as well. My bad. So for example, if we were to go to this example over here, and we had, I don't know, the peaks may be, let's just say 1, 1, 1, 2, 0, 0, 2, 2, 0, 3, 1, 1, 2, 2, 2, and 4, 0, 0, we can then determine the structure to be at FCC right off the bat. Yeah, so just determine that right off the bat, that's FCC. So, sorry, I'm brain farting right now. Yeah, and then another important formula that I do want to introduce is determine the interplanar spacing. So then let's just say, what was it? You're given this graph, and you want to determine the interplanar spacing present within the crystal structure based on that graph alone. What you can use, and there are different formulas used for different crystal systems. So then orthorhombic has a different system equation, tetragonal has a different equation. But for us, we're just going to focus on cubic because really that's the most common one. And that will be 1 over DHKL squared is equivalent to H squared plus K squared plus L squared multiplied by 1 over A squared. A refers to the lattice parameter. So the lattice parameter is essentially if you have a unit cell, this side distance will be the lattice parameter A. So this is for a cubic system. And inside the next video, I will actually be using the formulas. So then I know I kind of throw a whole bunch of formulas and rules at you. What was it? Well, what I'll do next video is that I'll post examples. I think I have 2 examples with crystal X-ray diffraction. So then you'll get to see me actually using these formulas, and the formulas will make a lot more sense. And it'll make a lot more sense on how we use the cubic system or cubic crystal system to figure out the interplanar distance. So DHKL, you'll figure out why it's important to know these different reflection rules for BCC, FCC, and simple cubic. And you'll also figure out why we use Bragg's law, why Bragg's law is important in the next video. Yeah. All right. I'll see you next time.